Let us start this lecture with a thought process by most influential physicist and Nobel laureate Albert Einstein, who says, "Try not to become a man of success, but rather try to become a man of value." It is indeed a very great statement which is out of the notion what we are having. All of us wants to be a man of success, but he says indirectly, if you become a man of value, the success will be coming to you in a natural way. So, let us keep this in mind and recall what we learnt in the last lecture. In the last lecture, we discussed about the injection distributor. As I told that there will be several injectors which will be placed or housed on the injector head, particularly for high thrust rocket engines. And now, what will be its configuration, and that plays a very important role in improving the performance of a rocket engine. There are several kinds of the injector distributors have been designed and developed by researchers across the globe, but we only discuss in the last lecture 4 representative one, and those are concentric type, honeycomb, alternative, and also the coaxials. If you see that there are several features what we had discussed, and later on we also looked at the processes involved during the combustion of hypergolic propellant and the non-hypergolic propellant. We had discussed that both are similar in nature. However, there is a distinct difference between the hypergolic and non-hypergolic propellant combustions, and the process are basically described in a very qualitative manner, and we have seen that there will be diffusion flame, there will be premix flame, there will be in between also, that is partially premix flame, there will be spray combustion, droplet combustions, and the turbulence level will be might be quite high. There will be all 3 modes of heat transfer and atomization and vaporization of the droplet, collision of the droplet, and coalescence of droplets will be taking place in the all together, and the flow will be moving at a very high velocity, and which will be varying from different zone to different zone that we had discussed. So, it is quite complex in nature, and that is why we looked at it little qualitative way. However, in practical situation, one can look at a gross effects, not getting into the very nitty-gritty about the phenomena which is occurring. So, what is being done in case of a liquid rocket engine, particularly by experimentalists, they look at how does the specific volume vary with time. As I had told earlier, that whenever the liquid will be vaporizing and its specific volume will be increasing, because it is in the vapor state, and also when the combustion is taking place, the gaseous products are formed, and then the vaporization also will be much higher rate, and specific volume also will be increasing. So, we will be looking at now the specific volume will be definitely increasing with time as the combustion, atomization, vaporization processes are initiated. And this process or this variation of specific volume with time definitely will be different for hypergolic propellant as compared to the non-hypergolic propellant. Therefore, let us look at how does the specific volume vary with time first for hypergolic propellant. So, This is the curve which is being shown here. This is a little qualitative in nature, that is specific volume versus the time in millisecond. You can see that as soon as the liquid propellant, both the fuel and the oxidizer, are injected into the combustion chamber of the rocket engine, then the specific volume will start increasing. This will be 0 at the time 0, and then this is increasing, and this slope looks to be very high, and it goes on because of fact that in case of hypergolic propellant, the fuel and oxidizer, whenever they will be coming in contact with each other, then there will be liquid phase reaction will be taking place. Generally, these liquid phase chemical reactions will be in fast order in nature, and then it will vary also fast, so that the specific volume increasing rapidly, and later on these liquid propellants will be converted into droplets and spray and then particulates, and then as a result there will be heat transfer, and the specific volume also will be increasing, but not at that rate what was occurring earlier. So, then it will be moving at a little slower rate, and it goes on increasing, and it becomes also slowed down with respect to time, and as it moves the various zones, you can look at that way, and then the specific volume increases asymptotically to the peak value, that is VV. And maybe you can say that combustion and the process is almost completed by this time. And this total time, if you look at, we can really look at the residence time. It consists of two times. One is the liquid combustion time, that is the thing which is required for the liquid phase reaction to occur, and that is TLC is the liquid phase time, and the other one is the gas phase time, that is the TRG, during which gas phase reaction will be taking place. So, it is not that easy to demarcate that. Generally what people do, that they made a slope to this initial portion of the reactions, or the initial increase of specific volume, and then when it will join this curve, then they call it this is TLC, and rest of the things are basically the residence time for the gas phase reaction. So, the total residence time consists of two terms in case of hypergolic propellant. One is TLC and other one is TRG, and this you can conduct experiment and look at it and find out and do that. So, let us look at what happens to the specific volume whenever the combustion, or whenever the liquid fuel is injected into combustion chamber, particularly for non-hypergolic propellant. In case of non-hypergolic propellant, when it is injected at A, then specific volume will be remaining almost constant around till the point B, that is the time, and later on due to vaporization, atomization, and also the liquid fragmentations, disintegration of the bulk liquid, there will be vaporization. So, there is a increase of the specific volume, what will be taking place very little bit, and then you start igniting the mixture, unlike your hypergolic propellant where ignition energy is not required initially, but in case of non-hypergolic propellant you will have to provide, but then it will take some time for the ignition to occur. So, it will be, and then C, and then of course, after this point there will be rise in the specific volume at a faster rate, and because the vigorous reaction is taking place in this region particularly, and then you can it reaches a saturated value at the peak values, and beyond that of course, there will not be much change as the most of the combustion might be taking place. So, at the point D, and this is the specific volume. So, in the similar manner we can also define this, the total residence time TR is a sum of the TI, this is the ignition delay time TI, and TRG is your residence time for the gas phase reaction. So, Ti, as I told, is the ignition delay time and Trg is the gas phase time, and this time must be provided, the total time, such that complete combustion can take place for a particular length of the combustors. And this is required little bit for the design, and as I told, the process is so complex that you cannot really simulate it numerically with the best model available at this moment, also the best computer in total. But however, one can do little bit model and look at it in a manner, but when you are designing, it is not really that easy to do that. So, you will have to rely on these semi phenomenological models that it can help you. So, let us look at that how we can use this residence time for deciding the combustion chamber geometry. And combustion chamber geometry means it can be have a length, if we consider a cylindrical combustion chamber with a diameter, and then in other words we will be looking at the volume of the combustion chamber. And it is very important because of fact that certain length must be provided in the combustion chamber for particular velocity, such that residence time will be good enough for completing the combustion. Therefore, it is very important. So, in order to ensure the complete combustion, we need to provide the minimum volume of the combustion chamber in case of a liquid propellant rocket engine, such that liquid propellant must have enough residence time to stay inside the thrust chamber, so that we can have complete combustions and you can get a higher thrust utilizing all the energy embedded in the propellant. Therefore, this is a very important one has to look at it. And let us look at a rocket engine. If you look at a diagram of that, and this you can say this portion, and this is your combustion chamber, and it is having a length Lc, and this is your diameter, I can say dc. So, from that I can get the area AC. AC is your cross sectional area of combustion chamber, and LC is your length of combustion chamber. Already I have told you, let me write down length of combustion chamber, and Vc is the volume of the combustion chamber. So, that means we will be interested to have a minimum volume, such that it will be compact one, and also at the same time complete combustion must be ensured. So, for that we will have to look at what is the residence time will be. Generally people use the characteristics length. This is your characteristics length of a combustor or the rocket engine, which is the characteristic length is basically of combustion chamber, and the characteristic length is a ratio of VFC divided by AT. AT is your throat area, and this is basically this is known as throat area. And VFC is the sum of VFC is basically Vc, that means this volume, and also from here to till this is I can call as basically the convergent portion of the nozzle. I can say nozzle NC, convergent portion of the nozzle, plus V nozzle NC, convergent portion of the nozzle. So, because people earlier days was considering that combustion might be taking place till the end of that. So, therefore, that effect has to be taken, that volume has to be considered in defining the characteristics length. And characteristics length is also dependent on the characteristics velocity can be related. So, we can really define a non-dimensional parameter known as the L star divided by C star. C star is your characteristic velocity. As we already have learned, the C star represent how good the combustion it is in a combustion chamber of liquid propellant rocket engines. And we had also defined the combustion efficiency using the characteristics velocity, and which is function of the Ti, the ignition delay, if I consider the non-hypergolic propellant, and when I consider the hypergolic propellant, I will be considering TLC, that is the time required for the combustion of liquid propellant or liquid phase combustion. And TRG is the residence time for the gas. So, that means L star by C star is a function of Ti plus a function of TRG. It is not that easy to evaluate it, that F1 Ti, and also this is generally smaller as compared to the TRG. Therefore, we can approximately say that it is a function of TRG only for the simplicity case. So, if I consider that, we can neglect this effect of Ti, that is ignition delay time, and consider only the residence time TRG, then we can define this L TRG, that is mg divided by m dot, that is m dot is basically mass flow rate of propellant, mg is the mass of the gas. So, and TRG we can write down, that is in terms of the average density of the gas, and VFC, that is the sum of the combustion chamber volume and volume of the convergent portion of the nozzle. And keep in mind that density will be changing along with the length of the combustors, because the and also the nozzle portion we are saying there will be change in the pressure as well, and therefore, we will be using the average value. And for that, what we will be doing basically, we can use this L star, this value over here in this expression, VFC is nothing but L star into AT and m dot. And if you consider that m dot and relate that thing into the C star, we will get C star is nothing but PC by AT. So, I can write down here in place of this, I can write down as basically PC AT and C star. So, AT will cancel it out, and I will get basically rho G L C C star P C. So, I would like to get expression for L star C star. So, what I will do, I will just multiply C star in the denominator and also in the numerator. So, that this becomes square, and then I will get L C by C star, that becomes P C divided by the rho G C star square into T R G. And we know that the L star by C star is nothing but your function of T R G. If you look at this P C rho G average C star square, you can find out that this is nothing but your gamma. Gamma is, capital gamma is basically gamma half and 2 by gamma plus 1 and gamma plus 1 divided by 2 gamma minus 1. So, generally the gamma for liquid propellant engine is taken as 1.2 for liquid propellant rocket engines. Of course, that depends on the type of propellant what you are using, but generally it is being taken as a majority of the liquid propellants. And keep in mind that this TRG is the some range what is being used for liquid propellant, for liquid propellants TRG is generally used something 2 into 10 power to minus 3 to 7 into 7 minus 3 second. So, basically 2 to 7 milliseconds, and this is some experimental values what we can get. And keep in mind that this we have neglected the Ti, and Ti the when we will include it is will be dependent on several parameters, and particularly of the injection system, because the Ti will be depends on the injection system, depends on injection system. And when you talk about this depends on injection system, that means it will be depending on the pressure across the oxidizer and across the fuel line. It will be dependent on the arrangement of the injectors and also the type of injectors being used, and it will be dependent on the turbulence level and also the type of propellant. So, therefore, it is really very difficult to a certain time or certain numbers. However, one can use the design data and include in this analysis. And we have also seen that L star, that means L star will be depending on all these parameters. Beside this, the people have also find out that L star also depends on the AC by AT ratio, and for 1 ton of the rocket engines, generally AC by AT around something 3 to 4 are being used, and for 1 ton engines, that means when force, the thrust level is 1 ton, and generally it is 2 to 3 is being used when F is 10 ton, and when F is 100 ton, that is something 1.2 to 2 tons are being used, that AC by AT in the range of 1.22. So, generally these are the data which are used by the American designer, that is ACAT in the range of 1.2 to 4, but generally the Germany people use little higher values because of fact that they want to make it a compact engines, and so because AC will be very higher, AT will be small, so that they can get a higher thrust. So, let us look at the characteristics length data, what we can see. These are from the experimental data, and you can see that chlorine and trifluoride hydrogen base, you will be getting something 50 to 90 centimeter as a characteristics length. And if you look at like liquid fluorine and hydrogen is something 60 to 70, and liquid fluorine to liquid hydrogen you can get the lowest one 50 to 66 centimeter, which is really very called for. However, it is not that easy to handle the liquid fluorine. However, you will get a higher value for the hydrogen peroxide and RP1. This is nothing but a kerosene, which is based on catalytic bed, that is a very higher characteristic length. Characteristic length means the length of the combustor also will be higher, and you can see that the liquid oxygen, liquid hydrogen will be getting little lower values, and of course, liquid oxygen and the gaseous hydrogen injection will be getting very low values. So, therefore, from this data you can observe that the characteristics length is not only dependent on the residence time for gas phase combustion, but also dependent on the type of propellant. So, however, this data is of characteristic length are being used by the designer, as the one cannot really relate to the other dependency factors that which are quite difficult to evaluate. And you must keep this in mind, the characteristic length which is being used very much by the designer, as I told. So, therefore, one has to be careful choosing this characteristic length, proper one, and with this we will stop over. In the next lecture, we will be discussing about other aspects of the liquid propellant system. Thank you very much.